Okay, I'm going to be honest. This is an algebra-based course, so there's going to be a lot of hand-waving stuff going on here. A lot of these things are really difficult to calculate. My goal is to help you understand the very fundamental nature of electric and magnetic fields, and so we're going to have to kind of say, this is how this works. So let's start with an example here. This is a magnetic compass. And so this works by interacting with the Earth's magnetic field, which actually has a very large downward component, but this is the horizontal component of the Earth's magnetic field. So that way is north. Actually, that's not north. Yeah, it is. Okay. Ha! Okay, that is north. And so actually I have here a tiny magnet, and you can see as I bring this in, the magnet interacts with the compass. So it changes the net magnetic field. This shows the direction of the magnetic field. Now, what if I take this battery and I connect a wire to it? So let's do this. So I'm going to hold this directly over the compass, and I'm going to connect the wire to the battery, and let's see what happens. It deflects. So it deflected this way. What if I put the compass on top of the wire, but I do the exact same thing? Oops, I got to keep that straight. Now it deflects the other way. So the magnetic field due to the wire is going this way on top of the wire, but it's going this way on the bottom of the wire. What if I put it off? Well, I can't really do that. Let's try this. What if I put it this way? What if I put it this way? What happens? Nothing. Nothing. So from this, we can kind of get a feeling for the pattern of the magnetic field due to a wire. And it looks like this. So we're going to get into stuff that's hard to draw because we're dealing with 3 dimensions. So one of the conventions we're going to use is this. These are vectors going in and out of the paper. So this is a vector that's going this way into the paper, and this is one coming out. So this is one way we can show directions in 3 dimensions. So let's say that I have this. That's my direction of the current. So it's coming this way towards the camera. In that case, I could have the following pattern of a magnetic field, and we use B to represent the magnetic field. So it makes this circular pattern around the electric current. So electric currents do make magnetic fields, and they make these circular patterns. So the current's coming this way, the magnetic field on top's going that way, on the bottom's going that way. So this is the first instance of the right hand rule, right? This is my right hand. So if you put your thumb in the direction of the conventional current, your fingers show the direction of the magnetic field. Okay. If I had a current going into the paper, then I would have the magnetic field on the top would go on that way, and on the bottom would be going that way. I know this is tough. Okay, I know that. Another thing that we can find is that as I move further away from the wire, the magnetic field decreases. So it'd be a smaller magnetic field over here versus there. We're going to get an expression. I'm going to give you an expression for the magnetic field due to a wire. But before that, I want to go into the magnetic field due to a moving point charge. Because remember, electric current is moving charges. So, but I wanted to show you that demo to show you that it actually does have a connection between electric current and magnetic fields.